So, have you ever looked really closely at, say, a fern or maybe a cloud,
Oh, yeah.
and you notice those incredible kind of repeating patterns? What if artificial intelligence could actually create those patterns, not just copy them, but, understand the logic behind them?
Right, get the essence of it.
Exactly. So today we're doing a deep dive into something called fractal hybrid image generation.
Sounds complex.
It is, but our mission here is basically to unpack how this intricate beauty of fractals is being merged with AI.
To create these really amazing new visual forms.
Yeah, and also look at why it's so challenging and, where this whole field might be going. We're using research notes you provided, so think of this as your shortcut to understanding this really fascinating intersection.
Well, let's do it.
Okay, so let's start right at the beginning. Fractals.
Yeah.
What are we actually talking about?
Well, fundamentally, think of shapes where the parts look like the whole thing.
No matter how much you zoom in.
Exactly. That's the key idea. Self-similarity. It means they look, well, equally rough at all scales.
Okay, so unlike, say, a smooth sphere, where if you zoom in enough, it just looks flat.
Right. With a fractal, like a coastline, you zoom in and you just find more and more detail, more jagged bits, more complexity.
Ah, the famous coastline paradox. I think I remember that.
Precisely. And what's really fascinating often is how this incredible complexity, this sort of infinite detail, it emerges from surprisingly simple rules.
Simple rules. How simple?
Like really simple recursive rules. You apply the same basic step over and over. That's how you get things like the Mandelbrot set or the Sierpinski triangle.
So it's repeating one instruction.
Pretty much. Or methods like iterated function systems, IFS, sometimes called the chaos game. You plot points based on simple rules, and eventually these beautiful, complex shapes emerge, like the Barnsley fern.
Wow.
And they even have this weird property, a non-integer fractal dimension. It's a mathematical way to sort of quantify just how complex and space-filling they are compared to normal shapes.
Okay. So that's fractals. Deep, complex, from simple rules. How does AI get involved? Where do they meet?
Right, so AI comes in through what we call deep generative models. These are algorithms designed to learn patterns from data and then create new realistic data that looks similar.
Like the AI image generators everyone's talking about.
Exactly. Things like Jan's generative adversarial networks, VAEs, variational autoencoders, and the newer diffusion models.
Okay, what's the difference, quickly?
Well, they have trade-offs. Jan's, they can produce incredibly sharp, very convincing images, but they can be unstable to train, and sometimes they get stuck generating only a few kinds of images. That's mode collapse. Not much variety.
Okay.
VAEs are more stable, good for smoothly blending between concepts, but often the images are a bit blurrier, less crisp than Jan's.
And diffusion?
Diffusion models are kind of the state of the art right now for quality and diversity.
Yeah.
Really amazing results. The downside, they're typically much slower to generate an image. Takes more compute time.
Got it. So we have these powerful AI tools. How do they start making fractals then? How do we bridge that gap?
Good question. There are basically two main paths people are taking.
Two paths.
The first is what you might call data-driven.
Meaning
You just take an existing model, like a Jan or maybe a diffusion model, and you train it on a big data set of fractal images.
So it learns what fractals look like.
Exactly. It learns the visual style, the textures, the patterns, and then it generates new images that look like fractals. We sometimes call these pseudofractals.
Pseudofractals.
Yeah.
Because they aren't generated by the actual fractal math.
Precisely. They mimic the appearance, but not necessarily the underlying generative process.
Okay, so what's the second path?
Now, this is where I think it gets really exciting. These are architecturally driven methods.
Architecturally driven.
Yeah, things like fractal generative models or FGMs. Instead of just showing the AI pictures of fractals,
You build fractal ideas into the AI.
exactly, you embed fractal principles like recursion, self-similarity, modularity directly into the structure, the architecture of the neural network itself.
Whoa. Okay, what does that actually do?
Well, one huge benefit is efficiency. The research suggests these FGMs can be incredibly fast, especially for high-resolution images. We're talking potentially like 96 times faster than some traditional models.
40 and 96 times. How?
Because they process information locally and recursively, much like a fractal is constructed, they don't necessarily need to process the entire massive image grid at once in the same way.
That's a massive difference. Real-time complex graphics, maybe.
Potentially, yeah. It opens up possibilities. There are also related ideas like using fractals as priors, where you use known fractal properties to guide an AI task, like improving image resolution, making images sharper.
Okay, building fractals into the AI sounds powerful, but I sense a but coming. What are the big challenges here?
Oh, definitely challenges. A major one is what's called the fractal inverse problem.
Inverse problem.
Yeah, trying to look at a fractal image and figure out the exact simple mathematical rules, the IFS parameters, say that generated it, that's proven to be NP hard.
Meaning
Yeah.
very, very difficult.
Meaning there's no known efficient algorithm to find the perfect solution, especially for complex fractals. We have to rely on approximations, clever algorithms that find good enough answers, but maybe not the absolute original recipe. It's like trying to perfectly reverse engineer a complex cake just by tasting it.
Okay, that sounds tough. So if it's hard to even define the ground truth rules, what does that mean for, like, measuring how well these AIs are doing? How do you evaluate success?
That's another huge issue. Our current ways of measuring AI image generation quality, things like FID scores, inception scores, they're mostly designed for photorealism.
Right, does it look like a real photo?
Exactly. They don't really care about or measure the unique geometric properties of fractals. Does it have true self-similarity? Does it have that infinite recursive detail? These metrics just don't capture that.
They probably don't capture how we perceive them either.
Not at all. They don't consider the cognitive load, how much mental work it takes you, the viewer, to process these incredibly intricate patterns. We really need new metrics, ones specifically designed for fractal geometry and maybe even human perception of complexity.
Makes sense. Beyond the tech challenges, any other hurdles? You mentioned legal stuff earlier.
Yeah, there are significant legal and ethical dimensions too, like copyright. Current law, especially in the US, following cases like Thaler v. Perlmutter, generally requires human authorship for copyright protection.
Meaning purely AI-generated art might just be public domain.
Often, yes. That's a huge discussion right now. And then there's the data itself. Training these models often requires massive data sets, and there are ongoing debates about the privacy implications and the use of copyrighted material in those training sets. It's murky territory.
Wow, okay, so let's try and wrap this up then. We've got this really dynamic field, right? Merging the kind of infinite complexity of fractals with the learning power of AI.
Yeah, pushing boundaries in computational creativity. The results can be visually stunning.
But the path forward is, well, complicated. You've got these big computational hurdles like the inverse problem, issues with how we even measure success, and these tricky legal and ethical questions hanging over it all.
Definitely. But that shift, the one from just mimicking fractals with data to actually embedding fractal logic into the AI's architecture.
That feels like the real game changer here. It's fundamentally different.
It really is.
So, thinking about this, what does it mean for you, listening? Could we see future AI systems that don't just make images, but genuinely understand and let us control abstract ideas like branchiness or spiralness?
Just by tweaking parameters in a fractal-based AI architecture, it's a fascinating possibility. Precise control over complex structures.
And then, how do we navigate the creative side, the legal side? When AI can generate art, potentially with infinite detail,
Yeah.
it really makes you wonder if the algorithms themselves start thinking, or at least processing, in a fractal way.
What new kinds of intelligence or even creativity might emerge from that?
Exactly. Something really interesting to think about.